just want to say hello, everyone, and thank you for joining us. Whether this is your first time with us or you've attended the previous session, we are glad to have you here for session 5, which is our final webinar in our series. Today's focus is on real-world applications and future innovations in chromatography. And before we begin, just a couple of quick notes. This session is being recorded, and you'll be able to access the full recording along with session 1 through 4 on our YouTube channel. If you have any questions during the presentation, feel free to drop them in the chat, and we'll have time at the end for a live Q&A. For those of you who are new, here's a brief introduction. We are a chromatography company based in Chicago area, dedicated to developing advanced HPLC column technologies and compact, easy-to-use mini HPLC systems. And with over 20 years of experience, we support labs around the world with custom method development and hands-on technical assistance. And if you ever need help with the challenging separations or want to explore new tools or have questions about your methods, don't hesitate to reach out. We're always happy to help. And with that, let's begin session 5. I'll go ahead and share my screen so we can get started. Hello, everyone, and welcome to the 5th and final session of our chromatography webinar series titled Real-World Application and Future Innovations. I'm Jovana Mitrovic, R&D chemist at Silk Technologies, and I'm excited to share with you some of the most advanced chromatographic solutions we have developed for real-world analytical challenges. And before we dive into today's content, let's just take a moment to recap what we covered in our last session, practical method development in mixed mode chromatography. We walked through the entire workflow of method development, demonstrating how analyte characteristics influence both column and mobile phase selection. We discussed strategies for method optimization and troubleshooting, and we worked through a complete example from analyte definition to optimized conditions, and explored real case studies from pharmaceutical, biotech, and complex sample applications. And finally, we emphasized the power of systematic screening and iterative method refinement. Here is our agenda for today. We'll begin by looking at the complexity of real-world samples and why traditional chromatography sometimes falls short. Then we'll introduce BIST, bridge ion separation technology, as a novel solution for polar and ionic compounds. Next, we'll discuss advanced biomolecule separations with BIST and oligonucleotide-specific innovations. We'll also explore HPLC, our dual-column approach for matrix cleanup, and showcase advanced mixed-mode columns like LIPAC and PVP. And finally, we'll look ahead to the future, the role of smart columns and molecular recognition in chromatography. Chromatography has always adapted to new challenges, but modern samples like serum, food extracts, and biological present unprecedented complexity. Polar and ionic compounds are very hard to retain with traditional methods. Conventional workflows often require multiple columns, strong buffers, or even ion pairing agents. And matrix interferences lead to poor reproducibility and reduced sensitivity. And today's talk is about innovation, about simplifying workflows, improving robustness, and enabling the resolution of coeluting or structurally similar compounds, especially for emerging analytes like degradants and modified biomolecules. And that's where mixed mode and advanced techniques come in. Let's start by talking about BIST. BIST, or bridge ion separation technology, is novel chromatographic mode that we developed at Silk specifically to solve a persistent challenge in analytical chemistry, retaining, eluting, and separating polar and ionic compounds, especially multi-charged. So let's start with the problem. Traditional reverse phase chromatography struggles with polar charged analytes. They elute too early with little or basically no retention, especially if they're charged. On the other hand, ion exchange chromatography often requires high salt concentration buffers, especially for multi-charge compounds that are hard to elute, which complicates the method, increases the viscosity of mobile phase, and can damage both columns and detectors. BIST offers a fundamentally different approach. It's a fundamentally new mode based on electrostatic interactions. It introduces a third component, a bridging ion in the mobile phase. This ion acts like a, let's say, molecular connector between the analyte and the stationary phase. It creates an orthogonal interaction that's tunable, selective, and very effective for multi-charged species. In practical terms, BIST reduces or eliminates the need for ion pairing reagents, simplifies the mobile phase, improves peak shape and retention for molecules that would otherwise either fly through the column or, on the other hand, get stuck in some columns. And this is especially valuable in many pharmaceutical biotech applications where many compounds are charged. So how exactly does BIST work? So let's take a closer look at the mechanism. Imagine a stationary phase that carries a fixed positive charge. Now, consider a positively charged analyte. Under traditional ion exchange conditions, or let's say ion exclusion, this analyte would be repelled by the stationary phase due to like charges, so resulting in no retention. But in BIST, things work differently. In the mobile phase, we introduce a doubly charged counterion, such as sulfate. This sulfate ion is negatively charged, and because of its dual charge, it can simultaneously interact with both positively charged stationary phase and the positively charged analyte. And this is where the key mechanisms come into play. The sulfate ion forms an ionic bridge between the analyte and the stationary phase, effectively overcoming the natural repulsion. It's a two-point electrostatic interaction that enables the analyte to anchor to the column surface despite having the same charge. One more critical factor here is solvent polarity. In highly polar solvents like water, ions are strongly solvated, meaning they're surrounded and stabilized by water molecules. And this solvation weakens their ability to form ionic bridges. But when we increase the organic content by adding something like acetonitrile, we reduce solvation. And the sulfate ions, for example, are now free to interact directly, which strengthens the bridge and improves retention. So at its core, BIST operates through cooperative mechanism, a doubly charged bridging ion connects the analyte to the stationary phase, and this interaction is enhanced in organic-rich, low-solvation environment. And this is what makes BIST uniquely powerful for retaining ionic and polar analytes that would otherwise be difficult to analyze in traditional modes. Here is a real example using dopamine. Dopamine is small, polar, positively charged molecule, and in the traditional reverse phase systems, it shows very little or no retention. If we take a positively charged column, such as BIST-B+, and we use let's say trifluoroacetic acid, TFA, as an additive, TFA provides single charge counterions. And this cannot form bridge. As a result, dopamine is not retained, it repels and elutes in void volume. Now, let's switch the modifier to sulfuric acid, which provides double charged sulfate ions. These ions can act as a bridge between the positively charged dopamine and positively charged stationary phase. And suddenly we observe retention. Dopamine interacts via these ionic bridges, which would be impossible under standard single ion conditions. We also observe that increasing the organic content, like acetonitrile in mobile phase, boosts retention even more. This reduced solvation, allowing the sulfate ions to participate more effectively in bridge formation. And the result, sharp, reproducible peak for dopamine in absolutely new mode of interaction. Now, if you want to develop a method using BIST technology, there are 3 essential rules you need to follow. Rule 1 is high organic content enhances retention. This reduces solvation of the ions and promotes bridge formation. We control retention by influencing the amount of the organic modifier in the mobile phase. For rule number 2, we have to include a doubly charged ionic modifier in the mobile phase, like sulfate or magnesium, for example. Single charged ions will not work. And last, rule number 3, the ionic modifier must be opposite in charge to both the stationary phase and the analyte. This ensures that it can bridge the two. These 3 rules are simple, and when applied correctly, they just unlock a very powerful retention mechanism for molecules that would otherwise defy separation. An important property of BIST is that retention is tunable based on charge of the analyte. The more charges the analyte carries, the stronger it interacts with the bridging ions and the longer it's retained. For example, a molecule with 2 or 3 charges will form a stronger bridge with a stationary phase than a molecule with just 1 charge under the same exact conditions. This means we can use charge density to fine-tune retention, optimize selectivity, and separate analytes that differ by, let's say, just a single ionizable group. And this charge-based control gives BIST a unique advantage, especially for polymers, oligonucleotides, and other biomolecules with variable ionization states. Now, let's look at 2 real-world examples to see how BIST handles multi-charged polymers in different analytical contexts. First, on the left, we have polylysine, a positively charged polymer that exists as a mixture of smaller molecular weight fractions. Using the BIST method with a positively charged column and sulfate as the bridging ion, we apply gradient from high to low organic content. This setup allows us to retain and separate the lower molecular weight fractions of the polymer effectively. And this approach is particularly useful when we're interested in fractioning the polymer, for example, during purification, quality control, or characterization of size distributions. The BIST mechanism provides the selectivity needed to resolve those subtle differences in polymer size and charge. Now, on the other hand, let's say our goal is different. Rather than separating fractions, we want to analyze or quantify the polymer as the whole. In this case, we use step gradient method, which is faster and very simple approach. So example here on our right, let's say PHMB polymer as an example. It's multi-cationic and very challenging to analyze using conventional reverse phase or ion exchange techniques, mainly because of its high charge density and polymeric nature. But with BIST, using a step change in organic content, we can achieve strong, predictable retention and clean elution, and all without high salt concentration in mobile phase or complex mobile phases. The reason we use an organic gradient in either continuous or step form is to control, again, the level of solvation. Higher organic content minimizes solvation, promotes stronger bridge formation, and better retention. When it's time to elute the analyte, we reduce the amount of organic modifying, weakening the bridge, and releasing the analyte from the stationary phase. And this is a major advantage of BIST. We don't need high salt concentration or complex buffers to elute multi-charged molecules, which are often required in traditional modes to use high salt concentration, especially in ion exchange. So that makes BIST easier to work with and highly effective for challenging examples. And together, these examples highlights the power of BIST to handle large, charged, and conformationally very flexible molecules, and something that traditional chromatographic modes often struggle to achieve. Oligonucleotides are unique and complex class of biomolecules. They are relatively large, highly polar, and carry multiple negative charges due to their phosphate backbone. These characteristics makes them particularly difficult to either retain, elute, and separate, depending on what mode, and using traditional chromatographic techniques. For example, reverse phase columns typically offer poor retention because there is minimal hydrophobic interaction, while ion exchange methods might seem more suitable. They often require high concentration of buffer salts to elute this analytes properly. And again, this leads to issues with peak shape, reproducibility, and just adds unnecessary complexity to mobile phase preparation. These challenges are exactly what bridge ion separation technology was designed to overcome. In this application, we use a negatively charged stationary phase, BIST-AC specifically, which is cation exchange column. Now, under normal ion exchange, ion exclusions conditions, a negatively charged oligonucleotide would be repelled by the like charged stationary phase, leading to no retention. But BIST changes that dynamic. We introduce a doubly charged cation into the mobile phase, in this case using TMEDA-formate buffer at low pH. These cations act as bridge ions binding to both the negatively charged oligonucleotide and the stationary phase, and this creates a stable ionic bridge, enabling retention that would not be possible in standard modes. In the example on the left, we are using an isocratic method where we carefully adjust the percentage of organic solvent to achieve a balance between retention and elution. On the right side, we demonstrate a gradient method going from high to low organic content to fine-tune elution. In both cases, we are analyzing 5-mer oligonucleotides, which are short fragments of the same length and number of phosphate groups, meaning they have same size and same amount of charges. However, we still observe different retention times. This is because chain composition also influences retention behavior. The basicity of nucleobases A, T, G, and C can affect the local charge distribution and interaction strength. Stronger basic groups influence the degree of negative charge on the adjacent phosphate backbone, which in turn affects how tightly the molecule interacts with the bridging ion and the stationary phase. So BIST is not only selective toward the number of charges, but also highly responsive to the chemical composition and functional group strength of the analyte. And this gives us a powerful tool for distinguishing oligonucleotide sequence that would otherwise be indistinguishable by size alone. So while BIST offers a powerful solution for oligonucleotide analysis, we wanted to take that simplicity one step further. So we developed a dedicated column called OligoMG. OligoMG operates on the same foundational principle as BIST, ionic bridging, but with a key improvement. It completely eliminates the need to add any bridging ions in the mobile phase. So here is how it works. The stationary phase in this column is negatively charged, just like the standard negatively charged BIST column. However, the surface is preloaded with magnesium ions, which are doubly charged cations. And this magnesium ion serves as built-in bridging agents. So now, when a negatively charged oligonucleotide enters the system, it no longer requires a separate ionic modifier in the mobile phase. Instead, it can immediately interact with the stationary phase via the prepositioned magnesium bridges, enabling effective retention through the same BIST-style mechanism. And the mobile phase becomes just much simple. All that's needed is basic water and acetonitrile. No buffers, no salts, and no pH adjustments. In this example, we show the separation of 3 negatively charged oligos of the same size using just water acetonitrile gradient. And the result is strong selective retention and clean separation without any need for method reoptimization or complex mobile phase formulations. And by having the bridge-forming ion directly into the column, OligoMG just streamlines the workflow, reduces method complexity, and brings the benefits of BIST to a just broader range of users and labs. And one of the most powerful and unique advantages of the BIST platform is the level of selectivity it provides when separating closely related oligonucleotide species. So let's break down what's exactly happening. BIST-based interactions happen directly on the surface of the stationary phase via the ionic bridges. Because of the surface level, highly localized interaction, the system becomes extremely sensitive to subtle variation in structure and properties of the analyte. This opens the door to a much more refined level of discrimination. And there are a few key ways this selectivity is expressed. One is molecular geometry. Even when oligonucleotides have the same sequence length and charge, differences in how the molecule is folded or structured in solution can influence how it interacts with the surface and the bridging ion. Charge density and distribution. It's not just about the number of negative charges, but where those charges are located and how strongly they're expressed. Even a slight variations in base composition or phosphate accessibility can influence retention behavior. Also, acid-base strength of functional groups. Some nucleobases are more basic than others, and this influences how the phosphate backbone expresses its charge, and therefore how strongly the oligo binds through the bridge. We can also distinguish structural isomerism. Oligos of the same length but different base arrangement, known as a sequence isomers, can exhibit different retention due to spatial and electrostatic differences, which are captured by the BIST mechanism. So what does this mean all in just like practically? It means you can resolve not just the full length target oligonucleotide, but also closely related impurities, including shorter sequences that result from incomplete synthesis, degradation products from chemical or enzymatic breakdown, minor structural variants or byproducts that differ by just a few nucleotides. So let's just take a closer look at these two examples shown in this slide to illustrate how oligo-MG and by BIST principle achieves this high selectivity. In the example on the left, we are separating 3 different 18-mer oligonucleotides. These sequences are the same length and have the same number of negative charges, but they differ in their base composition, that is, the specific nucleotides making up the chain. Even though they're structurally very similar, using oligo-MG column, we are able to resolve them using just very straightforward gradient from 65 to 40% acetonitrile. And this shows that the retention is very sensitive, not just to size and charge, but also the sequence-specific differences, such as variations in base strength and distribution of charge along the chain. On the right, we see a separation of 10A oligonucleotide, a sequence made of 10 adenines, and its shorter byproducts, which can appear during synthesis. And despite the close similarity, the oligo-MG columns resolve the full-length product from these shorter fragments using, again, very simple, straightforward gradient from 75 acetonitrile to 50% acetonitrile in mobile phase. So together, these examples highlight how BIST technology enables fine-tuned separation based on both structure and composition and using simple organic gradients. And this level of selectivity is especially useful for applications like synthesis monitoring, purity checks, and impurity profiling of oligonucleotides. Let's now talk about lipids, which pose a unique challenge in chromatography due to their diverse structures. And one of the most difficult areas is lipidomics, where we need to separate a wide range of lipid species, from completely non-polar to more complex amphiolic molecules like phospholipids. Phospholipids, for example, have polar head groups and non-polar fatty acid tails. And this amphiolic structures makes them difficult to resolve on traditional reverse phase columns. And the challenge with traditional reverse phase columns is that they rely only on one hydrophobic interaction to separate compounds. And that works to a certain point, but it creates serious limitations. For example, let's say you have a neutral lipid and a phospholipid, both with the same fatty acid chain length. On the reverse phase columns, they may show very similar retention because the column doesn't interact with their, for example, polar functional groups. And as a result, these very different molecules could collude, making it hard or even impossible to distinguish between them. And that's why we developed the LIPAC column, a mixed mode HPLC column that provides an ideal balance of retention forces for lipid analysis. LIPAC combines a reverse phase hydrophobic retention with a strong polar negative group, enabling to interact with both non-polar lipid tails and charged or polar head groups, and all within a single stationary phase. And it's optimized for high organic mobile phases like methanol or ethanol with some amount, very small amount of buffers such as ammonium formate. And these conditions support lipid solubility and elution while maintaining just excellent peak shape without need for ion pairing agents or just complicated mobile phase systems. And the result is a true one-column solution for comprehensive lipid analysis, capable of separating both hydrophobic neutral lipids and amphiphilic lipids in a single run. And here are two examples just demonstrating the LIPAC column's outstanding performance across different lipid classes. In the right chromatogram, we separate a variety of phospholipids. These amphiphilic molecules often have very similar structures, may share the same fatty acid chain length, but differ only in their polar head groups or vice versa. And such a subtle differences typically cause coelution or poor peak shape on conventional columns. And with LIPAC, however, we achieve excellent resolution with sharp symmetrical peaks under high organic conditions and using LSD as detection method. And on the other hand, in the left chromatogram, we analyze triglycerides. These compounds are highly hydrophobic, and with their retention behavior influenced by fatty acid chain length and degree of saturation, by using just simple gradient from 50-50 methanol-ethanol to 100% ethanol in mobile phase, with LIPAC column, we obtain strong retention and clear separation for these compounds. And this versatile capability to effectively separate both charged polar lipids and neutral hydrophobic lipids makes LIPAC just an ideal choice for comprehensive lipid profiling in food science, biomedical research, and pharmaceutical applications. Next, let's look at PVP, a synthetic polymer widely used in pharmaceuticals and cosmetics industry. PVP is incredibly difficult to analyze using standard chromatography because of its amphiphilic nature, polymeric structure, and tendency to stick to column surfaces. It can show very strong adsorption and conformational variability, and even carry over from run to run, which leads to inconsistent peak shapes and just unreliable quantification. To address this, we develop a dedicated PVP column that specifically optimized for accurate and reproducible analysis of PVP and similar polymers. And our solution handles all the typical challenges. It provides complete elution, no more binding or ghost peaks. It tolerates the flexibility and variability of the polymer chain. It delivers sharp, clean peaks even at low concentration and using for LSD as the detection. And the mobile phase is very simple, which is not usually the case when we want to analyze polymers. We use a simple step gradient from 100% water to 50-50 water acetonitrile mix and 20 millimole ammonium acetate buffer in mobile phase. And this gives us just robust method, sensitive, works reliably across a range of concentrations and polymer molecular weights. And that's why if you ever struggle to get PVP off your column or even detect it at all, this column offers just a real practical solution. Now let's shift to a completely different but equally powerful innovations. HPLC, our dual column chromatography platform designed specifically to tackle sample matrix complexity in real time. And in many real-world applications like food, biological fluids, or environmental samples, we don't just face challenges from the analytes themselves. We also face complex, interfering matrices, proteins, fats, pigments, salts, all of which can fold the column, distort the signal, and just reduce reproducibility. At the heart of HPLC is a very sophisticated valve system that precisely controls the flow path between two columns arranged in series. First is the flip column positioned upstream of the analytical column. This is specialized column and it's dedicated to trapping problematic matrix components such as proteins, fats, pigments, which are often present in complex real-world samples like food or biological fluids. And following the flip column is the analytical column, where the actual separation and detection of our target analyte takes place. The valve's role is crucial. It dynamically switches flow paths at specific times during the analysis to enable both sample cleanup and analytical separation seamlessly within one run. And this dual column valve controlled setup enables inline matrix cleanup without the need for extra offline sample preparation steps, guard columns, or manual cleanup procedures, just greatly improving throughput, reproducibility, and column lifespan. So let's see how HPLC operates. HPLC operates through two tightly coordinated phases controlled by the valve timing and solvent delivery. So phase one, which is sample loading and trapping. So upon injection, the sample flows first through the flip column. This column with tailored mixed mode chemistry selectively retains matrix interferences such as proteins, lipids, and other sticky or hydrophobic contaminants. Meanwhile, our target analytes, which can be typically smaller, more hydrophilic ionic species, pass through the flip column with no retention and proceed directly to an analytical column for separation. This selective retention allows the flip column to act as an inline trap, holding back compounds that could otherwise fold the analytical column or interfere with detection. Now, phase two, which is valve switches and backflush. After precisely time delay optimized for complete analyte transfer, the valve switches position. And at this point, the analytes are securely in the analytical column for reliable separation and detection. And because of this valve switch, no material from the flip column flows forward into analytical column. Instead, now the mobile phase flows backward through the flip column while still flowing in the normal forward direction through the analytical column for analysis. And this backward flow isolates the flip column, ensuring that only the analytes of interest, what we are analyzing, reach the detector and preventing any contaminants from passing through. And for example, if additional cleaning of the flip column is needed after the run, we can always use, for example, pump B that can, let's say, deliver strong organic mobile phase to backflush the flip column further. And flushing all this retained contaminates directly to waste. And just this black flush step prevents falling and buildup on the flip column, ensuring that matrix interferences just never reach the analytical column. And when we initially inject the sample, most of the matrix contaminants get trapped right at the front of the flip column. And because of this, when we switch the flow to backward during backflush, it becomes much easier to remove these interferences effectively. And they just rarely reach the end of the flip column, which greatly reduces the chance that they will ever enter our analytical column. Now, let's look at how HPLC performs in real-world food analysis, for example, specifically in samples with complex organic matrices like wine or fruit juice. In our first example, we are analyzing metabisulfite in red wine. Now, wine is just notoriously very difficult matrix. It contains tannins, sugars, pigments, organic acids, alcohol, all which can interfere with the analyte detection, especially when working at low concentrations. And using the HPLC setup, we inject the wine sample, and it first passes through the flip column, which in this case is prime sub-100 column that has reverse phase functionality plus negative charge. And under initial low organic mobile phase conditions, the flip column retains most of the matrix interferences, the color compounds, sugars, polyphenols. Meanwhile, the metabisulfite analyte, which is small, polar, negatively charged, passes through the flip column and enters the analytical column, which is prime sep SB, that has reverse phase functionality plus positive charge, where it can cleanly get separated and detected. When we inject the sample, after a short delay, about 1.1 minutes, the valve switches. The method, and that's when we backflush our flip column. The method used here is gradient and goes from low organic to 50-50 acetonitrile water. And the flip column is backflushed, and all the retained matrix is directed to waste, never contaminating the analytical column. And here you can also compare it to the same exact method, but using only prime sep SB. There is no flip system at all, there is no flip column, which is our blue chromatogram. And you notice how chromatogram that utilizes flip system, the red one, is much cleaner. Now, in the second example on the right, we apply the similar approach to ascorbic acid in strawberry juice. And again, strawberry juice as the food source, it's full of sugars, pigments, and a lot of other compounds that tend to stick to the column or mask the signal. Again, the flip column here traps these matrix components during the loading phase. And at around 0.5 minutes, the valve switches and the flip column is flushed clean, while the analytes flow through the analytical column for analysis and detection. So what's important here is there is no offline sample preparation required, no solid phase extraction, no chemical cleanup. HPLC enables direct injection of complex food samples and still gives us clean, reproducible chromatograms. Now, let's shift to a much more demanding matrix, human serum, and see how HPLC performs when analyzing polar biomolecules directly in biological fluid. The target analyte in this case is serotonin, a small, highly polar neurotransmitter that's notoriously difficult to retain and detect in serum, be it using traditional techniques or, let's say, reverse phase column. And there are two reasons for that. Serotonin is too polar and elutes too early with no meaningful retention on regular traditional reverse phase columns. Serum itself is full of proteins and lipids that contaminate the column, interfere with detection, and just cause carryover and falling. With HPLC, we overcome both issues. And here is how. First, the sample we used is just diluted serum. Is injected and enters the flip column, which in this case is PRIMESEP-SB with mixed mode functionality, contains reverse phase, plus positive charge embedded. The mobile phase at this stage is low in organic content, allowing the flip column to trap serum proteins and hydrophobic interferences. At the same time, serotonin, being small, hydrophilic, and positively charged, passes through the flip column unretained and moves into analytical column, which is PRIMESEP 200, that has reverse phase functionality plus negative charge, where it's retained and separated under optimized gradient conditions. And as soon as we inject, after short delay, about 0.8 minutes, the valve switches and the flip column is backflushed, and this sends all trapped proteins and contaminants to waste before they can reach or damage analytical column. Now, here is the question I want to leave you with as we look ahead. Have chromatography columns truly reached their limit? For decades, most columns have relied on one or maybe two interaction types. And for a long time, that was enough. But the reality is that approach has limitations, especially when we are dealing with today's complex real-world samples. And a lot of people assume that every possible interaction, column, or method has already been discovered. But we disagree. Molecular complexity, whether it's in biopharmaceutical, food samples, or environmental matrices, keep pushing the boundaries of what chromatography needs to deliver. And this is where mixed mode chromatography stands out. And by leveraging multidimensional interactions at the same time, hydrophobic, ionic, polar, we unlock levels of selectivity and flexibility that just aren't possible with single mode columns. So no, innovation hasn't peaked. In fact, it's just getting started. And today, when we talk about smart columns, we are really talking about mixed mode columns. And they're truly changed what's possible in chromatography by combining all these multiple interaction mechanisms into a single column. They've opened the door to separating a much broader range of analytes in complex samples. And that includes everything from small neutral molecules to highly charged biomolecules, all within real-world samples like plasma, food, or wastewater. And this approach made columns more robust, more capable of handling a wide variety of mobile phases and dramatically increasing their selectivity and capacity, often 10 times greater than what traditional single mode columns can offer. And that's what exactly makes them smart. But mixed mode doesn't just solve problems, it creates new opportunities. It gives us a platform to build on. Because of mixed mode, we can now start imagining even more advanced columns that can adapt, handle virtually any analyte, no matter how complex or sensitive, columns that eliminate the trade-offs between resolution, speed, and matrix tolerance. So smart columns aren't the final destination, they're the reason we can now aim even higher. And looking ahead, one intriguing possibility is development of what we might call molecularly intelligent columns. And inspired by nature's just remarkable way of recognizing molecules, like how antibodies specifically bind to antigens. These columns could someday